Yeah, now I want to demonstrate how to do a random labeling analysis with the data of José. Here we use his data of droppings of animals, and the data structure is that we have some droppings that have seeds of a particular species and others have no seeds of this particular species. So my data structure is like this. So this is the data file which you need to prepare to run this analysis. It's a very simple structure. It's an ASCII file. And in the first line, you have basically the information on the size of the observation window. So these are the 0 and 1059. So this is the X size and this is the Y size. And then in total, you have 328 data points. So 328 different droppings. And then you see in the first column you have the X coordinate, the second one you have the Y coordinate, and then the third and fourth column simply indicate if you have a 1, 0, that means it contains seeds of the species of interest, and if you have a 0, a 1, then it does not contain seeds. Yeah, so this data structure can be used for the random labeling analysis. In this case, I want to know, is there any spatial structure of droppings that contain seeds relative to all droppings? Yeah, and now to run Programita, you go to the folder that contains the data and Programita. And then you have basically simply to double-click the Programita Excel version. There's also one file in, this is this res file, this is a result file. And this gives you all the information you need to repeat the analysis. And it also documents you the results of the analysis. Yeah, but here in this case, now I want to do a step-by-step presentation. So you first have to double-click Programita. Then Programita software opens. Then in the next step you have to go to this small input data window and to select the data file. And then in the next step you have to define the spatial resolution of your analysis, which basically is the bin width. And the analysis here proposes you a bin width of 10, but it turned out that it's nicer if you have a slightly smaller resolution, so we selected in the paper a bin width of about 3. Yeah, and then you click OK and then calculate index, and then you see here the spatial pattern. So the red dots are droppings with seed and the green ones are the ones without seed. Yeah, and here you already see the percolation function. This is the univariate percolation function of the droppings with seeds, and this is the bivariate percolation function. Yeah, you see the percolation function looks slightly rugged. It's not very nice, and this happens because the ring width is too small, so then you have not enough data points to get a nice statistic. So that means you go here to ring width, and in this particular case we selected a ring width of 5. And now if you run it again, then you see now you have a nice smooth function, and this allows for better inference. Yeah, now you have almost everything there. You only need to select the suitable null model. So then you go here to calculate simulation envelopes, and then this window opens where you can select the null model. Then you go, of course, to the random labeling null model. And then you run again, and then you see here the null model patterns. And again, you see the results. So this is the univariate percolation function, and you see the simulation envelopes and the mean value of the null model patterns. Yeah, in the paper we didn't use the percolation function directly. We used the transformation of them. We used the mark connection functions because they show the spatial effects much better and in a way, true way, the spatial structure of the droppings at themselves, because this is a conditional analysis. It's always conditional on the spatial structure of all droppings. And we want to know, is there a structure of the seeds inside the droppings? For this reason, we select this mark connection functions, and this is in this case here. You go to the P12, and then you click here, this small OK, and then you get now the other summary function, which shows very nicely that up to maybe this distance about 100 meters, there's a positive spatial correlation in seeds inside all droppings. So to remember, the mark connection function basically looks at pairs of droppings which are a certain distance away, and then calculates the probability that both of them have a dropping in. So this would be the univariate one. And you see there's a very strong aggregation. And you see this also a bit here. For example, here, that means the droppings with the seeds, there are lots of quite aggregated here, and also there's some aggregation here. Yeah, and then you also see the bivariate mark connection function. So this is the probability that the first point has a dropping and the second point has no dropping. And then interestingly here you see in a way spatial independence. So there seems no association of points without droppings to points with droppings, but you have only an aggregation of droppings, of seeds inside the droppings, as you can see here in the univariate case. Yeah, so here we did 39 simulations. This doesn't give you very good statistics, so it's better to do more. For example, using 199, or even you may use 999. In this case, the 5% simulation envelopes are obtained if you use the fifth lowest and highest. Yeah, and then you go again here to calculate index, and then it shows you again all the random labeling null model patterns which are used now to estimate the simulation envelopes. And then you will see now the result, and this is now basically the same as before, but you see of course a nicer, smoother simulation envelopes. It's also possible now with Programita to look at the global envelopes. So for this you go here to this small box, goodness of fit, you click this, and then if you want to have the univariate analysis, you go here, you select student, this gives you the student transformation, and this gives you then the pointwise envelopes here, and it gives you now the green ones, which are the global envelopes. That means you have a significant departure from the null model if the observed curve is at least at one distance outside the global envelopes. And this is the case for many different distances. You see there's a really strong departure from the null model. For the bivariate case, so this you click then again here and then calculate again. Then you see there's also only a very weak departure. So all distances are very well inside the simulation envelopes. Yeah, so this was now the example for random labeling, and you only have to take the data and the Programita, and then you can very easily replicate this analysis. Yeah, and finally I show you how to use this results file to just repeat the analysis. So to do this, maybe just go here, load settings, for example, you click there. And then you find here this file figure 3DEF res. And this is the results file corresponding to these figures in José's paper. And then if you go there of OK, then it automatically loads the settings of this analysis. And then you have only to go calculate index, and then it repeats the analysis. Yeah, so I wish you lots of fun using Programita for this specific analysis.